So this is now our second day of review, and we are going to start with chapter 8. And our first, concepts are on page 192. Oliver's here, so let me just add that quickly to the attendance. Okay, just made it in the nick of time. Okay, so yes, I'm here and I'm not absent. I kind of assumed they were the same, so a little redundant, but I got you. So on page 192, we talk about the difference between a population, a sample, and a sample design. The population, of course, is everything under that you care about, whether it's people or cars or flowers or grains of sand or stars in the universe. It could be anything, but the population is all of them. A sample is some of them, the ones that I'm collecting information from. And then we have a sampling design, which is your method by which you are going to take your sample. And we saw that there were different designs that we could use. The first one on page 192 is a sample survey, which is not usually a good one, but sometimes all you can do because surveys do happen. So a sample survey is one of them. On page 194, we talk about one of the things to be on the lookout for when you're taking a sample, which is bias. We do not want to have a biased sample. I don't want to ask people their favorite sport at a Lakers game. I don't want to ask people what their favorite flower is at the United Rose Lovers Foundation dinner or whatever. You want to make sure that there's no bias in your sample. On page 195, there are two concepts. The first is a voluntary response sample. A voluntary response sample is not one of the good ones. And the other one is a simple random sample, what we call an SRS, which is, as hopefully you know or remember, the best type of sample, SRS. And slow me down, stop me at any time if you need to catch up or if I'm going too fast. On page 196, we have the concept of random digits. And if you recall how we used random digits to help create simple random samples or help to simulate simple random samples. On page 198 was the idea of random digit dialing. Thank you, old man. So random digit dialing on page 198. And these are all qualitative. Yeah, daily pasta. These are all qualitative, by the way. There's no math in these, right? These are all the different terms. So you can just turn to the appropriate page and read the sentence, and it really explains what these things are. And then on page 199 is basically the entire point of statistics. A random digits is a method by which you can create a random sample. So like I assign different digits to people and then randomly pick them. So you have, everyone put everyone's name in a hat and pick one out. Random digit dialing is a way of dialing random phone numbers. Random digit dialing. Page 199 is the concept of inference. The whole idea of statistics is that you infer information about the population from taking information about the sample. The inference is the whole purpose of statistics. On page 200, we had some other types of samples. We had a stratified random sample. And even though a stratified random sample can be abbreviated SRS, don't do that because SRS is already something else. With a stratified random sample. And we had multi-stage samples. A multi-stage sample might be something along the lines of, well, first let me stratify them, and then once I do that, let me do an SRS. Or first, let me do this, and then I'll do this, and then I'll do this, and then I'll do this. And you kind of keep breaking it down into stages. It's a multi-stage sample. On page 202, we talk about a few problems that you might have when taking samples. One is undercoverage, not getting enough to represent the entire population. Undercoverage, you're not covering the entire population. For example, if I'm interested in the average whatever of every American and I only ask men, that's undercoveraging. I'm missing out on a very significant portion of the population. So undercoverage. Non-response is when people don't respond, right? I've picked a sample of 1,000, but 300 of them don't respond. So my sample is now only 700. That's not good. I wanted a sample of 1,000. I have non-response. There could be response bias. Okay, for example, I remember helping someone in stats a couple months ago, and they had a very nice question about, it was posed to African Americans about whether or not they think the average Caucasian is racist. And they got a very different answer depending upon whether the interviewer himself was African American or Caucasian. So there's bias inherent, not in the sample itself, but in the interviewer or the way it's worded. There's wording bias. There's many reasons why a sample might be biased, and you should be aware of all these. They're all on page, or some of the reasons are on page 202 and 203. The last stuff was the impact of technology. I kind of skimmed that, so don't worry about that. It's not going to be on the test. So that takes care of chapter 8. Are there any questions about any of the stuff from chapter 8? Very qualitative. There's no math in chapter 8, right? Other than the random digits on a single number. So hopefully that makes sense. And then we move on to chapter 9. And chapter 9 continues with where we left off from chapter 8. We have on page 214, we have the difference between an observational study and an experiment. An observational study is where you just observe information, versus an experiment where you actually do something to elicit data. So for example, if I think that smoking might harm babies, pregnant mothers smoke or drink and then might harm babies. I can't really take 1,000 women and say, okay, you 500 smoke and drink and you 500 don't, and let's see what happens to the babies, right? That's not really something that you can do and get away with. So the best you can do is say, oh, I have data from these 500 women who unfortunately smoked and drank during pregnancy. Let me look at their children compared to these 500. So you're observing data without actually performing an experiment. So the difference between an observational study and an experiment. Also on page 214 is the concept of confounding. Confounding is when you have two variables that might both influence the results, and you can't really separate which one is having an effect and which one is not, or how much of an effect one does. They're confounded. They're jumbled together. You got to separate them. So confounding is a bad thing, right? We don't want to have confounding. For example, if I'm investigating heart disease, I might want to look at things like diet and lifestyle, and at the same time, I might want to look at something like, how much they drink, for example. Those both might influence how susceptible they are to having a heart disease, and I want to be able to separate those out. So when variables are confounded, that can cause problems. On page 216, this is also very qualitative. On page 216, when you do have an experiment, you have the individuals. Those are the people in the experiment that you are studying. They're often called the subjects of the experiment. And quite often, I'm looking at the factors that might influence the result. The factors of an experiment are the various things that I might change which have a say in the outcome of the experiment. And what I would normally do is apply a different treatment to different groups. So a treatment, which is also defined on page 216, is a combination of values of factors. So if I think that there's two different factors that might have something to say, I might create 4 different treatments, having both factors, having just this factor, having just this factor, and having no factors. So the treatments are the way I set up my experiment so that each individual or each group of individuals gets a different treatment based upon the various factors that I think might play a role. So factors and treatments, these are defined on page 216. When you do perform an experiment, this is page 219 now. When you do perform an experiment, you will have the control group, and then you will have the treatment group or groups. The control group is the one where you're basically saying, let's not give these people any specific treatment because we want to compare the different treatments to them. They are the control group. And then the different treatments can all be compared to the control group. Also on page 219, we have the idea of a randomized comparative experiment. Very wordy. A randomized. I'm sorry?
Can you say it again?
A randomized comparative experiment. So the random part means that people are distributed randomly into the different treatments, and then we want to compare the results. All right, it's a randomized comparative experiment. You don't get to come in and say, yeah, I know you're comparing people who work out to people who don't, so I want to be one of the ones who works out, man. Okay, bruh. You can't do that. It's like, I will decide. I will randomize who gets what treatments, and then I can compare the results. Because if you're coming in and you're saying that you want to be in a certain group already, that means you might have a predilection for that factor, and that is not really what I'm looking for in the experiment. I want to have something that's more random in that regard. So a randomized comparative experiment, I'm comparing treatments, but I'm distributing the treatments randomly. On page 220, we talk about a completely randomized design. A completely randomized design is in which all the subjects are randomly given different treatments. Okay, a completely randomized design versus a partially randomized design. I don't see the words partially randomized design here, but yeah, I mean, they act like the stuff before that wasn't completely randomized, but it was. It's just a concept. A completely randomized design might be redundant. It might be the same as an SRS or something else. A completely randomized design just means everyone is randomly given a different treatment. Nobody is assigned something with any intention. The most famous are the double-blind experiments where neither the person doing the experiment or the person upon whom the experiment is being done knows which treatment they're in. Okay, a double blind. They're blind. They don't know if they're getting the placebo or if they're getting the real thing. And the experimenter doesn't want to treat people differently depending on whether they're getting the real thing or the placebo. So both sides are blind to it. On page 223, we have the 3 basic principles of experimental design. We want to control any lurking variables. We want to randomize the subjects. And we want to use enough subjects. You can't do it on 2 people and say that your experiment works. It's got to be on a large enough sample. So control lurking variables, randomize the subjects, and make sure their sample is large enough. Those are the 3 basic principles of making an experimental design. This next one on page 223, a big one, we use this a lot. What does it mean for a result to be statistically significant. A result is statistically significant if it was very unlikely to have occurred just by chance. Okay, if I have a fair coin and I flip it 1,000 times and it comes up a heads 1,000 times, that is a statistically significant result because the likelihood of that happening on its own is so small as to never happen. What would I conclude in that case? It's probably not fair to begin with. I would question my original hypotheses, which is all what statistical significance testing was all about, as we saw. On page 224, these two terms that everybody mentioned, placebo and double blind, they're both mentioned on page 224. On page 226, we talk about matched pair design. We talked about that later in terms of the matched pair t-test, where you match them up like left hand to right hand or before to after. And we talked about block designs. So, for example, I might block all the men and women together but separate because all the men might have a similar features in one regard, all the women might have. Maybe I want to block by state. Maybe I want to block by this or block by that. It's very similar to a stratified design. In fact, I really even wouldn't worry about it because it's not going to be in the test. So don't worry about block designs. But for completeness sake, it is there on page 226. So that takes us to the end of chapter 9. We didn't do this thing on data ethics because I have no ethics. So I didn't teach this chapter. It's not going to be in the test. Chapter 10 looks to be a chapter on review. So there's no new material. So before we move on, are there any questions with what we've done so far? All good? All good. All right. So let's move on. I think we skipped a bunch of chapters here in fact. And I believe we skipped all the way now to chapter 15. And this is like the heart of statistics, chapter 15. So on page 334, and again, I will pause just to make sure that there are no questions before moving on. One five. Quince. Right? Is that 15? Quince? I don't really speak Spanish very well, but I'm pretty sure that's correct. We have class next week on Tuesday. That's right. Our third day of review will be Tuesday. Isn't that great? That way you get to have me one more time. Aren't you lucky? I guess you're not responding, so I don't know what that means. But anyway, so on page 334, we talk about the difference between a parameter and a statistic. Oh, we are happy. Oh, no. Well, thank you. So on page 334, we talk about the difference between a parameter and a statistic. A parameter and a statistic. What's the difference between a parameter and a statistic? Anyone? Well, it's on page 334, so I hope you know it. A parameter and a statistic. So a parameter is something about the entire population, and a statistic is something about the sample. Statistic is a number that refers to a sample, whereas the parameter is a number that refers to the population. Parameter is the sample, so that was not good. Parameter is not the sample. All right, a parameter refers to a number that comes from the population, and a statistic comes from a number that from the sample. So that's on page 334. Then we have the law of large numbers. The law of large numbers for proportions in particular is on page 336, the law of large numbers. Anyone recall what this very important law of large numbers says?
Is it the bigger the sample size is, the most like the closer you are to the actual mean, and it looks more like a bell curve?
Well, the bell curve part was actually something else. That's the central limit theorem. But the first part, what you said was correct. The larger the sample, the closer your sample average is to the actual average. And in this case, the closer your sample proportion is to the actual proportion. So this is a law of large numbers for proportions, and that's on page 336. On page 339, we talk about the concept. Can I repeat that? Which part? The whole thing? The law of large numbers says that the larger the size of your sample, the closer your statistic is to the parameter. Whatever it is that you're measuring, the closer it is to a true value, essentially. Which is why we take large samples, because we want it to be more accurate. On page 339, we talk about a sampling distribution. And if you recall, I played for you that applet a while back of some weird looking distributions, and then what those distributions look like when you take larger and larger samples. That led to the central limit theorem, but the idea is that the shape changes depending upon the size of the sample. So a sampling distribution is essentially the shape of the distribution when you take samples of a given size. And that's on page 339. And then on page 340, finally, after like a half an hour of qualitative stuff, we now have some math. On page 340, we have the mean and standard deviation of the sampling distribution of p hat. Again, p hat is the sample proportion. And because I don't know what my sample is going to be before I take my sample, I don't have a value for that in advance. It's a random variable. It can be lots of different things. And on page 340, they give us the mean. Yes, it is the mean and standard deviation of a sample proportion. The mean and standard deviation of a sample proportion. So they define p hats, which we've used quite often. P hat is the number of successes over the size of the sample. And they also give us the formulas for the mean and standard deviation of p hat. What was the mean of p hat? Or the mean of the sampling distribution for p hat? Anyone recall what the mean was? The mean is the same p, it's the actual true value, which is why we use it to approximate the true value. And the standard deviation was p1 minus p over n, which popped up in a bunch of formulas that we ended up using. p1 minus p over n, this is all on page 340. And then on page 341, we have the fact that as the sample size increases, it becomes closer and closer to being normal. That's on page 341, including the rule of thumb for when you're allowed to use it. Just so you know, that's when n times p and n times 1 minus p are both what? Anyone recall? N times p and n times 1 minus p are both what? Ten or more. Excellent. Greater than or equal to 10. And that takes us to the end of chapter 15. So now we move on to chapter 16. Chapter 16 talks about confidence intervals. So we will start with I'm just looking for the summary and not for every little thing. Can you repeat the cognitions, please? What's a cognition? I feel like I'm in a minority report. What do you mean by, you mean conditions? The conditions are that the number of successes and the number of failures must both be greater than or equal to 10. Now on page 350, we have the 3 conditions which must be satisfied before we're allowed to infer from the sample to the population. 1 has to be from an SRS. 2, we don't know P. If we did, why are we taking the sample? And 3, the number of successes and the number of failures both must be greater than or equal to 10. If you have those, then you are allowed to infer from the sample to the population. On page 353, we have the idea of a confidence interval, which we had a number of chapters on, a number of formulas for lots of different cases. And you should certainly on the test have all of those handy. But there was a confidence level. Usually we did 95%, 90%, 99%. Those are the 3 big ones. The confidence level. We had the margin of error. That's the plus or minus part, and how much it can go in either direction. You want to be able to interpret a confidence interval. What exactly does it mean? And then finally, on page 356, we have the formula for the confidence interval for a population proportion. Anyone recall what it was offhand? P hat plus or minus what? What was the formula for a confidence level? We are on page 356 now. Anyone recall? P hat plus or minus Z star times the square root of P hat 1 minus P hat over N. We use this one a lot. How do you find Z star? How do you find Z star? Anyone? Are you guys, can you hear me? Am I deaf? Not am I deaf? That won't make any sense. Am I mute? This thing's not coming out, or what's going on here? Comes from the table. Well, yes and no. Yes, in theory it does, but you shouldn't have to use the table because you should know how to find Z star. What's Z star for a 95% confidence interval, for a 90% confidence interval, for a 99% confidence interval? What are Z stars? Well, if you don't know that, you should. So make sure you look it up. And FYI, it's 1.645, 1.96, and 2.56, I think. I never used that one, but anywho, on page 357, we have the concept of the standard error. The standard error, which is important because sometimes problems will give you the standard error and will not give you the margin of error. So you should know the relationship between them. On page 362, we have the formula for calculating the sample size for a given margin of error. Margin of error includes the z star, standard error does not. The difference is the z star. Margin of error is z star times the square root of p hat 1 minus p hat over n. And the standard error does not include the z star, but it does include everything else. What about the sample size for a desired margin of error? M equals. That little blurb is given on the top of page 362. You certainly want to have that formula. In fact, that whole box, because there's 2 pieces of information there. On page 363 is a little warning. The margin of error does not cover all types of error. What are the only types of error that the margin of error covers? We went over this, I remember. The margin of error only covers sampling error that comes from the randomness of the situation. It does not come from more practical errors like non-response or under coverage or some of the more qualitative ones. On page 364, we have the +4 confidence interval. The +4 confidence interval. I'm not going to go into the details because it's all in the book and I've done it before, but the +4 confidence interval, when you use it, what are the conditions? And that takes us to the end of chapter 16. Are we everything good so far?
Yes.
Any questions? Okay. So let's start then chapter 17. Chapter 17 is on significance testing. And we start on page 376. On page 376 is the idea of a hypothesis test, a null hypothesis, alternative hypothesis, one-sided hypothesis testing, two-sided hypothesis testing, all that stuff. Stuff that we use lots and lots and lots of. All of that stuff is on this page, on page 376. On page 378, is the concept of a test statistic as well as the p-value. Now, hopefully you know or remember the p-value because we used that pretty much on everything after this point in the book. P-values dictated all of our confidence intervals, and not a confidence intervals, but hypothesis testing. So very important stuff. Hopefully you all remember that stuff. If not, you know what to look over. We talked about on page 381, the significance level of the test, alpha. Usually, what is alpha? Usually alpha is 5%. So what's the relationship between p-value and alpha? Someone tell me, what's the relationship between the p-value and alpha?
The p-value is lower than 5%, then you don't have enough evidence that the null hypothesis is correct. And then if it's higher, then you don't have enough evidence that the null hypothesis is... No, you have enough evidence that the null hypothesis is right.
I mean, I hear what you're saying, but the wording is a little off. If the p-value is less than alpha, the evidence supports the fact that the null hypothesis is wrong. The evidence actually supports that fact. The evidence is there, it's conclusive. Whereas if the p-value is greater than alpha, then the evidence is not conclusive. But yes, Grace, the p-value measures the probability of getting a more extreme value than the one you got from the experiments. If the p-value is greater than alpha, then you accept the null hypothesis, or at least you do not reject it. We don't accept anything. We don't reject the null hypothesis. It might still be wrong, but we just don't reject it. Okay, we don't reject the null hypothesis. And if the p-value is less than alpha, then we do reject the null hypothesis. It's about rejecting, never accepting. And Sydney, it's about whether or not the evidence supports the fact or not. Right? Does the evidence support this, or does the evidence support that? So that's on page 381. On page 383, we now have the formula for calculating our test statistic for a significance test involving a proportion. It looks very similar to the confidence interval for proportions because they're connected. There's a deep connection between them. But that test statistic is given on the bottom of page 383. It's also given on the front cover of the book, but you'll find it on page 383. And 384. The blurb is half and half. It's half on page 383 and half on page 384. Excuse me. On page 387, what's on 383? 383 to 384 is the formula for the test statistic. That's the one that you're going to use to compute your p-value. The p-value is the probability of getting more extreme value than the one you got. What is the one you got? That's your test statistic. That's essentially it's a z-score. And that's on page 383 to 384. On 387, it talks about the difference between a statistical significance and a practical significance. Just because a result is statistically significant does not automatically mean that it's practically significant. And that takes us to the end of chapter 17. Any questions so far? Again, I'm not explaining everything again. I am just essentially telling you where you can find the things that are important. That is 17. So now we are on chapter 18. On 18, we are comparing our study of proportions, but this time we are looking at two proportions, not just one, but two proportions. And usually what happens with two, can you repeat what test stat relates to p-value again? If you look at a normal curve, the test statistic is where you fall on that curve. The p-value is in the probability of being past it, or possibly past it and double it for both sides if it's a two-sided test. So the p-value is the probability of being more extreme than your value, and your value is the test statistic. And every different scenario has a different test statistic, okay? So in chapter 18, for example, we talk about the two proportions. What page are we on for chapter 18? So we are now on page 399. On page 399, we talk about the sampling distribution for a difference of proportions. So the last couple chapters ago was a sampling distribution for one proportion. Now we have the sampling distribution for a difference of proportions. And on page 399 is a formula for its mean and its standard deviation, both of which we use in the formula on page 400. On page 400, we have the formula for the standard error of a difference of proportions. And we have the formula for the confidence interval for a difference of proportions. This is all on page 400. The confidence interval for a difference of proportions, the standard error, it's all there. in the green box on page 400. On page 404, we have the significance test procedure for a difference of proportions. In particular, we have the test statistic for a difference of proportions. That's on page 404. And just like we had the +4 confidence interval for one proportion, we also have the +4 confidence interval for two proportions, and that you can find on page 407. And this takes us to the end of chapter 18. We are moving right along. I think this is wonderful. So wonderful, in fact, that I think we've done like 10 chapters today. And maybe that's a little enough to wrap your head around, and we saved the last 5 or 6 for Tuesday. What do you guys think about that? Rather than just throwing in tons of more. This is already a significant amount for one day, I think. And this will give you 5 days. Hopefully you're not waiting to prepare for like the day before the final, but you're actually going to start or have already started. And you have 5 days to go over, all the stuff that we did today, and then we can do the rest of the stuff on Tuesday. But also don't forget, there's new homework up, the last homework of the year. The final is open book, open notes, and open calculator. It's not open person, so don't get help from other people. But barring that, it is open book, open notes. So everything that I'm giving you, all these formulas that I'm telling you should know, you should have them all at your disposal. Don't wing it. You have the opportunity to make sure that everything is in the right place. All my proportion formulas, all my double proportion formulas, all my mean formulas, all my double mean formulas, or maybe you want to do it by all my confidence interval formulas, all my statistical testing formulas, all my different ways of calculating, getting a sample survey, all the problems that I might have. Lump things together into categories so they're easier to find. But most importantly, don't just say, well, I'll have all the formulas written down, so I'll be fine. You should know what those formulas are so that you don't have to think like, wait, am I allowed to use this one here? What's this one again? What does that thing mean? You should know those things so you can have it in front of you so you don't have to memorize them, but don't just completely wing it. All right, so I think we've had enough for one day. I'm going to stop recording.